Let's look at problem 12 from the Fall 25 final exam. There, we are given a matrix X whose columns have already been mean-centered, meaning that the average of each column of X is 0, and we do this whenever we are performing PCA, that is, we mean-center our data to bring it to the origin. And we're given that X, this mean-centered version of it, we've taken its singular value decomposition into U sigma V transpose. X is a matrix with 24 rows and 3 columns, which means sigma is also a matrix with 24 rows and 3 columns. The first few rows of sigma looks like this, look like this, and the matrix V transpose looks like this. And we know its first and third rows, but we don't know V transpose's second row. And so now we're asked several questions about X. Also, let me just note the shapes, as I said before, of sigma are 24 by 3, and V transpose are 3 by 3, is 3 by 3. The first question is, what is the rank of X tilde, or this X? And the answer to that is 2, because in general, the rank of a matrix is equal to the number of non-zero singular values it has. So this one we can kind of just read off from sigma. The fact that we have a 0 here tells us the number of non-zero singular values is 2, which means the rank of this X is 2. The second part says, it is possible to find the vector V2 or V2 transpose, however you like, without knowing any other information about X, which seems a little counterintuitive. But the reason we can do it is because we know that the matrix V must be an orthogonal matrix, meaning it must satisfy VV transpose is equal to V transpose V is equal to the identity matrix, which here would be the 3 by 3 identity matrix. Okay. What this means is that the columns of V must all be orthogonal to each other, and the rows of V must all be orthogonal to each other. Just as a refresher, in general, V transpose V is a matrix that contains the dot products of all pairs of columns of V. And so the off-diagonal elements will be the dot products of 2 different columns, and the diagonal elements will be the dot products of columns with themselves. So the fact that this is the identity, with 1s on the diagonal and 0s elsewhere, tells us that the columns of V must be unit vectors, and they must be orthogonal to each other. So 2 different columns must have a dot product of 0. VV transpose tells us the same condition must be true of the rows. Anyways, so here, what we know is that the rows of V transpose and the rows of V must be orthogonal to each other. So this missing vector here just needs to be orthogonal to both the first row, 1 over root 10, 3 over root 10, 0, and the last row, 0, 0, 1. Now, one way you could do this is by using the cross product, but on an exam, it would be ideal to think of an answer that's a little less involved than doing that. And what I notice is that if I place values in the first 2 components of this vector, well, then that vector will be automatically orthogonal to 0, 0, 1. Because if I put, it doesn't matter what I put in the first and second components, I'm going to dot that with a 0 and a 0 in the last row. So if I do that, then I can just focus my attention on placing value, on making my vector orthogonal to the first row. Here's what I mean. If the first row is 1 over root 10, 3 over root 10, 0, then all I need to do for my second row is say something like negative 3 over root 10, 1 over root 10, 0. Is that orthogonal to the first row? Yeah, it just sort of swaps the elements and makes one of them negative. So if we dot these, we'll get negative 3 over 10 plus 3 over 10, which is 0. So those would be orthogonal. And of course, this would be orthogonal to 0, 0, 1 as well. So this is one answer for the second row of V transpose. Are there other answers? Yes, but there's really only one possible other answer, and that would come from swapping the minus sign from here to here, because we know this also has to be a unit vector. Okay? There are only those 2 unit vectors that are orthogonal to both V1 and V3. And I've shown you those 2 options. Okay, one way to think about this is that V1 and V3 span a plane in R3. And we were looking for a unit vector that is orthogonal to this plane. And so there's only two options. Either we can take the one that points upwards, out of like above this plane, or the one that points below this plane. And those were the two options we just looked at. Okay, great. The next part asks us to really understand where the components of the singular value decomposition come from. Okay, it's a true or false question. Does there exist a vector z such that xtz equals 2z? Well, if we take a look at this, what is this really saying? It's asking whether z is an eigenvector of xxt with an eigenvalue of 2. Because what's happening to z when it gets multiplied by xxt is that it just gives us back a scaled version of z. So it's asking, is z an eigenvector with an eigenvalue of 2? So what this is really asking is, does xxt have an eigenvalue of 2? And what's the answer to that? This is kind of meant to be a trick question because we see a 2 in the sigma, but remember, the sigmas, that is the singular values of x, are the square roots of the eigenvalues of xxt, which are the same as the eigenvalues of xtx. If we ignore the fact that one of those two matrices, xtx or xxt, will have the 0 eigenvalue just repeated more times. But the non-zero eigenvalues between xxt and xtx are shared. So, back to the big idea here, the answer to this question is no. The non-zero eigenvalues of xxt are 12 squared and 2 squared. So xxt has an eigenvalue of 4, but not of 2. So if the question instead asks, is there a vector z such that xxtz equals 4z, the answer to that would be yes. But because we had a 2 there, or any number that wasn't a 144, a 4, or a 0, the answer is false. Okay. The last part. What is the largest possible variance of the components of xw, where w is a unit vector in R3? Largest possible variance of xw, where w is in R3. This is asking us to really understand how principal components are formed. So the main idea here is that principal components are found by finding the directions in our data along which the data varies the most. So if our data, which is mean-centered, looks something like, I don't know, this, a very robotic-looking data set, but you get the idea. If that's what our data look like, the direction of the first principal component, and remember, principal component is just a fancy term for new feature, the direction of the first principal component would look something like that. I don't know, right? And that's the direction along which the data varies the most. And as we see in the notes, that is also the direction along which, if we projected all of our data points onto the line in that direction, that is, if for each data point, we found the point on this line that is closest to the data point, those projected those errors, would be as small as they could be on average across the whole data set. The main idea here is that minimizing mean squared orthogonal projection error is the same as maximizing how spread out the projected data points are. Anyways, what does all of this have to do with the quantities in the question? The main idea is that the direction along which the data varies the most is the first column of v in the singular value decomposition of x tilde. So the first column of v is the direction along which the data varies the most. The second column of v is the direction along which the data varies the most while being orthogonal to the first column of v. So the next best direction has to be orthogonal to the first direction, and that's a consequence of the columns of v being orthogonal. So in this question, what we're really asked is to find what the variance of the first principal component is, okay? And so instead of considering all possible w's using this logic, we know that the w that maximizes the variance of xw is v1. Okay, and really we're asked for the variance of the first principal component, okay? And another formula to note is that the variance of a principal component is equal to the singular value for that principal component squared divided by the number of data points that we have, okay? What is all of that here? Well, the first singular value is 12 here. So 12 squared is the number in question over the number of data points we have in total, which is 24. This looks like 12 times 12 over 24, which to me looks like 6. So the answer to what is the largest possible value of the variance of xw, where w is any unit vector in R3, is 6, because the unit vector in R3 that makes the variance of xw as big as it can be is v1, where v1 is the first column of v in the singular value decomposition of x tilde. In other words, it's the eigenvector of xtx with the largest eigenvalue. Okay, so that was problem 12 of Fall 25's final exam. Let us know if you have any questions.